friends, in this lecture we will talk about the working principle of n-channel GFET. N-channel GFET, the constructional details we have studied already in the previous lecture. So now how n-channel GFET works. What is the principle behind the working of n-channel GFET? So when we apply a battery to drain and source terminal, this battery is called as VDD, and the voltage it establishes is called as VDS. That means the voltage between drain and source. So when we apply a battery VDD under the condition that VGS is equal to 0. So this is first condition. That means no voltage is applied at this gate terminal, or you can write it as this. That means this gate is connected to ground. So VGS is 0 and VDS is applied. VDS is applied. So in this condition, when VGS is 0 and VDS is applied and it is increased, then what will happen? This is drain current ID, which will flow through this n-type region, which is called as channel, and on the x-axis let us show VDS when VGS is 0. So as we can see that in this JFET, these are P regions and this is N region. Therefore there is a depletion region between P and N here, and the depletion region between P and N here. When we will apply VDS, then this terminal will become more positive than this terminal, as the positive terminal of the battery is connected to this terminal and source terminal is grounded. Therefore the width of the depletion region is more here towards drain in comparison to the width here, that means towards source. So width of the depletion region is more here towards drain end, and width of the depletion region is less here at the source end. Now when voltage is applied, and if we increase the voltage, this VDS, if it is increased, then current start flowing like this, and if we keep on increasing the voltage, current also increases. But what will happen then? This depletion region also increases on increasing the voltage, because as you increase the positive potential, this depletion region will also increase. So when we increase VDS, this current increases and this depletion region also increases, and after a certain amount of applied VDS, this current becomes constant, and this all is happening under the condition VGS is equal to 0. The voltage at which this current becomes constant is called as pinch off voltage, and the current is called as IDSS, drain source saturated current. When VGS is equal to 0, it is called as IDSS. This is condition 1. Condition 2 is, before going to condition 2, let us try to understand why this current becomes constant. As we have seen that on increasing voltage, current is increasing, but simultaneously the potential barrier is also increasing, so channel is getting narrower, and if we keep on increasing the voltage, channel narrowing is also increasing, and at a certain point when channel is at the verge of getting closed, and at that time the current becomes constant, and that voltage at which this condition occurs is called as pinch off voltage. Pinch off voltage. This region of the graph is called as ohmic region, and this region is called as saturation region. And this characteristic curve is called as drain characteristic curve, of JFETs. Drain characteristic curves of JFET. This is all about condition 1. Now we'll talk about condition 2. What was condition 1? Condition 1 was VGS is equal to 0. That means gate terminal is grounded and VDS is applied. Then what happened? Current start increasing, and after a certain value of Vp, current becomes constant, and that value of Vp is called as pinch off voltage, and that value of current, which is saturated current, is called as IDSS. Now the second condition is, if we have applied VDS under the presence of VGS, then what will happen? The voltage between gate and source is VGS, and between drain and source is VDS. So in the previous condition we have seen that on increasing VDS, ID increases, and in the condition when VGG is 0, at a certain value of voltage it becomes constant, which is called as pinch off voltage, and this is called as drain source saturated current. Now if we have already applied some value of VGG, that is some gate voltage has already been applied, then what will happen? This gate voltage is reverse biasing this PN junction. We can see that negative terminal is connected to P, So this is reverse biasing this junction. That means even before the applying of VDS, the width is somewhat more. Even if we have not applied VDD so far, but because of the application of this VGG or due to this VGS, there is already a depletion region present, a bigger depletion region present, and when we apply VDD or VDS, then the width of the depletion region once again starts increasing, and after some amount of voltage it becomes constant. That means some VGS is, this is under the condition VGG is equal to 0, and when some VGS is applied, then the drain source saturated current, maximum drain current, you can say that it is like, it can be drawn like this, and its value is less than IDSS. If a bigger voltage is applied here, then this current saturates at some once again lower value. So if we keep on increasing this VGS, a condition will occur when ID will become 0, and that voltage of VGS, when drain current will become 0, that voltage is called as VGS off. So this is drain characteristic curve of JFET, N channel JFET. And the second kind of characteristic curve which we are going to discuss now is transconductance curve or transfer curve. Transfer curve or transconductance curve. These are characteristic curves which tell us about the behavior of the device. Drain characteristic curve is plotted between ID and VDS when VGS is constant. So drain characteristic curve like this, VGS is constant and transconductance curve is plotted between ID and VGS. So drain characteristic curve is plotted between drain current and drain source voltage, and transconductance curve is plotted between drain current and gate source voltage. As we have seen that gate source voltage affects the drain current. So let us see what will happen if VGS is 0. If VGS is 0, we have seen earlier also, when VGS is 0, maximum value of drain current is IDSS. So when VGS is 0, ID is IDSS, and if we increase VGS, that means we are increasing the width of the depletion region which is blocking the channel, which is blocking the path of the flow of electrons, then drain current start decreasing, and if we keep on increasing this, then at a certain value of gate source voltage, drain current becomes 0, and that is called as VGS off. This is called as transconductance curve of field effect transistors. In the next lecture, we'll talk more about field effect transistors. Thank you.